Hi everyone. Today we're going to be discussing Deutsch's algorithm in quantum computing. The problem is as follows. Suppose we have some function f and we want to know some characteristic about this function f. We don't care about what the function is, we don't care about how the function is computing its output, we just care about some property about f. Specifically, we want to ask, is f balanced or constant? So it's an unknown function f, right? We don't know anything about it, and we just want to know whether it's balanced or constant. So balanced means that you have an equal number of zeros and ones in the output, and constant means that you have either all zeros or all ones. Again, remember that we are restricting ourselves to functions f that take a single binary input and produce a single binary output. So either 0 or 1 for the input and either 0 or 1 for the output. So let's take a look at the 4 possible functions that we can have, since we're restricting ourselves to binary functions. So if you look at this first one here on the left, you have a column for x and a column for the output f of x. So as you can see, the output is 0 regardless of the input, and likewise the function right next to it, the output is 1 regardless of the input. However, on the third function, f3 of x, it produces its output based on its input. So this is the identity function. So when x is 0, the functional value or the output is also 0. And when x is 1, the functional value or the output is also 1. And for the fourth function, when x is 0, it outputs 1. And when x is 1, it outputs 0. And so this last function looks really familiar, right? Well, this is the not function. It's inverting its input. And as you can see, these two functions right here are constant. So this is the constant 0 function and this is the constant 1 function. Whereas this is the identity function and it's balanced because you have an equal number of zeros and an equal number of ones. And this function is also balanced, and it's because you also have an equal number of zeros and an equal number of ones. So, yes, so the two on the left are constant and the two on the right are balanced. And now let's discuss Deutsch's problem. So, given an unknown unary function that is either balanced or constant, you want to determine which it is in only one query of the quantum oracle U of f. So, we are going to need to discuss what a quantum oracle is and what it does. So, here's an example of a quantum oracle U of f, and basically it is a black box. You don't know anything about how it's working or the underlying circuitry, but you do know that this is the output. And this top wire is called the data register, and this bottom wire is called the target register. Upon giving an input x and input y, the quantum oracle U of f, so it computes some function f, it will produce some output, produces x, and it produces y, binary added with f of x. So remember that this f is the function that is unknown, and it's in question as to whether it's balanced or constant. So why is something like that useful if you don't know anything about the function f? Well, because it will compute f for you, right? So if we were to set the input into the target register, or where y was, if we were to just set that as 0, then this is what our quantum oracle would output. It would output x and f of x. And that's because, you know, previously here we had y binary added with f of x. Well, when y is 0, 0 binary added with anything is the thing. And let's see why. we have 0 binary added with 0 gives you 0. 0 binary added with 1 gives you 1. And so you might just be wondering, okay, well, if there are only 4 functions, then we could just, plug them in and do this manually. Or you can just evaluate f of 0 and f of 1, and you'll know right away whether the function is balanced or constant. And so that means that it's going to take 2 evaluations in the classical case. But Deutsch's problem says that we're restricting ourselves to only one evaluation, or one query to the quantum oracle. And so how are we going to solve this? Well, here's Deutsch's solution. And this is a circuit which, for some f, some unknown function f, will tell you whether f is constant or balanced based on the output of this measurement here, which will either output 0 or 1. Now, this might look a little scary at first and not very intuitive, but let's discuss why this is how it is and what are the fundamental principles that are underlying this. And we'll see shortly that it's actually very, very clear. So there are actually 2 techniques that are used in Deutsch's solution. The first is quantum parallelism, and the second is the phase kickback trick. First, let's just talk about quantum parallelism. Quantum parallelism uses superposition to evaluate multiple states at the same time. And that's because if we were to restrict ourselves to, suppose, just these two, so if you have a single bit, it can either be in just the 0, it can either be 0 or it can either be 1. And so that's analogous to the classical 0, and this one's analogous to the classical 1. If your bit can only be either one of these, right? But quantum computing has this cool feature which is called superposition, and it lets your single qubit be in superposition. And that's, you have a linear combination for the state of a single qubit. So it's somehow in both of these states at the same time. So quantum parallelism uses this superposition feature to evaluate multiple states of the bit at the same time. Okay, so that means that we can't just be working with 0 and 1. We want a superposition of them. And so that's achieved by passing the 0 and 1 states through the Hadamard gate. So if you pass that shouldn't be an arrow, but you actually get this state. So when I pass 0 through the Hadamard gate, it transforms it into a superposition of both the 0 and the 1 state with some constant, multiplied by some constant. And when I pass 1 to the Hadamard gate, it gives me the following superposition. Root 2. Oops, sorry. Okay, so that kind of explains this first area here. But why are we passing in, remember 1, when you apply h to the 1, then you get, here you get minus, and here is plus. So the question is, okay, why are we passing minus here into the target register of the quantum oracle? Well, that's going to be because of a trick called the phase kickback trick. And basically what's going to happen is it's going to cause the information about f of x to be kicked back into the output of the data register. And let's see why that is. Okay, so let's just talk about the quantum oracle really fast so that we can kind of get a better understanding of what's going on. So recall that this is the quantum oracle, and when given this set of inputs, it produces this set of outputs. And so if you want to see that, if you want to see that algebraically, u of f applied to x tensored with y is equal to x tensored with y binary added to f of x. And remember earlier we said that the phase kickback trick, instead of passing y, we're going to pass, for y, we're going to pass the minus state. So let's see what happens when we do that. This is not clear. Okay. So applying u of f to x tensored y gives us the following, and that's just, we're just plugging in y. Then that's going to be equal to this, because you can distribute the x, right? And then apply the u also through distribution. And so then the result is going to be x tensored with 0 binary added to f of x minus x tensored 1 binary added to f of x over root 2. And remember, this is because right here we said this is the output, x tensored with y binary added to f of x. So here our y was 0, here's f of x, but in this case our y was 1, and here's binary added to f of x. So remember what we said, right? 0 binary added with anything is that thing. And so, And so right here we get f of x, and 1 binary added to anything is the opposite of that thing. So that's f bar of x. And that's because if you say 1 binary added with 0, the result is 1. 1 binary added with 1, the result is 0. Okay? So now we can factor out the x, and this is going to be the result. F of x, so x tensored with f of x minus f bar of x over 2. Now let's think about what are we trying to solve again, right? We're trying to say if f of x is balanced or constant. Well, in the case that f of x is equal to f naught of x, then disregard balanced or constant. But when f of x is equal to 0, so this becomes the 0 minus 1 over root 2. And we know that 0 minus 1 over root 2 is the minus, right? And if f of x is 1, then you have 1 minus 0. And that looks like this. Right here. Right? You might want to pause the video and see that for yourself. Okay, we can actually factor out negative 1 raised to the f of x, and we'll get this. You get x multiplied by negative 1 raised to the f of x times this. And it's just simply factoring out a negative 1 raised to f of x. Now remember that this is a scalar, So we can actually pull it out to the front here. And so that's what we do here. Just a more compact version. So negative 1 raised to the f of x times x tensored with this. Oh, sorry. And we know that this is just the minus ket. So in this way, we've successfully managed to kick back the information about our function into the output of the oracle at the top. Now, here, instead of passing a single value into the data register of the quantum oracle, remember we said that we want to pass a superposition. We want, instead of passing just the 0th state or just the 1 state, we want to pass both at the same time. And that's achieved by passing the plus state. So now what we're going to have is as follows. UF applied to remember that the plus state is right? We'll just keep that, we won't expand this, but this is the expanded plus state and this is the minus state. And that's going to equal and that's because, as we did before, we can just distribute, and then apply the U of f. And going off of our result from before, we have that this is going to equal to negative 1 f of 0 And remember, all of this is happening in a single pass. So look right here, we evaluate f of 0 and f of 1 at the same time. This is all over root 2. And we'll factor out the minus. All over root 2. Okay. And so by combining the phase kickback and quantum parallelism, we've managed to get an expression that contains both f of 0 and f of 1 in the top register of the quantum oracle. So it's in a single register. And so now we can ask the question that Deutch posed in the context of this simple expression. What is the difference between the balance case when f of 0 does not equal f of 1 and the constant case when f of 0 equals f of 1? Well, why don't you pause for a second and try to figure it out. So let's see, when they're constant, the two terms in the numerator have the same sign, right? So when it's constant, suppose f of 0 is 0 and f of 1 is 1. Sorry, I said constant. So f of 0 is 0 and f of 0 is 0. So negative 1 raised to the 0 is 1. So this has a positive sign. Negative 1 raised to the 0, this also has a positive sign. Okay, what if f of 0 is 1 and f of 1 is also 1? Then this is going to be negative 1 times this ket plus negative 1 times this ket. So they both have the same sign when it's constant. Okay, what if it's balanced? So f of 0, suppose, is equal to 0 and f of 1 is equal to 1. So balanced means that they have different signs, because this is when f of 0 equals 0, then this is positive. When f of 1 equals 1, then this is negative. Now flip it. When f of 0 is 1, then this is negative, and when f of 1 is 0, then this is positive. So in either case, when it's balanced, then the numerator has the terms in the numerator have different signs. And so we can compact this by writing. And so it can be written more succinctly as follows. Remember, if they have the same sign, then it's constant, and that's if f of 0 equals f of 1. And if f of 0 does not equal f of 1, which means that it's a balanced function, then the terms in the numerator will always have different signs. And you can see that by if you multiply by positive 1, then the sign of this is positive and the sign of this is negative. If you multiply by negative 1, the sign of this becomes negative and the sign of this becomes positive. If we can see then that this collapses to this. Oh, sorry. Oops. Forgot to write that. Because this is the plus state, right? And if we multiply by, and this is the negative state. And so we have this result. Okay? And remember what we said earlier. The output of the oracle, given some input x and minus, is going to be equal to, something times the negative ket. And so we know that the output of the oracle at the top is the actual output, and the output at the bottom can be ignored, because we know it's always going to be the minus ket. And so, right, so you're going to get two possible outputs, the plus or the minus at the top. And you're always going to get this in the bottom wire. Okay, and so what we know then is that if it outputs this, then the function f is constant, and if it outputs this, then the function is balanced. But suppose we want to measure it in the computational basis, where we have zeros and ones instead of plus and minuses. So what we're going to do is we're going to apply the Hadamard gate again to go back to what we started with. Because remember, applying a gate twice, a quantum gate, because it has certain properties, it's unitary and Hermitian. So applying the gate twice gives you back what you had before. And remember that we fed into this, where are we? We fed here, we're feeding 0 and 1, right? And so we're going to apply the Hadamard gate to this top output to get back to either a 0 or a 1. And we just ignore this because we know it's always going to be the negative ket. And so going back here, remember we're going to either have plus or minus at the top wire because of what we have here. Then applying the Hadamard gate to this gives us the 0 back and gives us the 1 back. Then if we measure it in the natural basis, if we see a 0, that means that the function was constant. And if we see a 1, then the function was balanced. And again, just to recap, something that might not have been clear was that this is the output of the oracle. And the bottom wire is always going to output a negative, but the top wire is going to output either the plus or the minus ket. And we're going to take the output of the top wire and apply the Hadamard gate to it. So when the output of the top wire is a plus and we apply the Hadamard gate to it, we get back to the 0, and when the output of the top wire is a minus and we apply the Hadamard gate to it, we get a 1. Then when we measure, if we see, because remember we're measuring here, right here. After we apply that H to the top wire, we measure. And so if we see a 0, then that means that it's constant, because to see a 0 means that you had to have a plus, and to see a plus means that f of 0 equals f of 1, aka it's constant. So it's constant if you see a 0, and it's 1 if you see a balance. And so that concludes Deutsch's algorithm. It's really using superposition to get a speed up, a double speed up basically. So in classically what you had to evaluate twice, now you can just evaluate once. And so it might not seem like a big deal now because we're dealing with such trivial functions, but when you have input of variable length, like suppose an input string of length n, then evaluating all of that in a single pass gives you a huge performance advantage and reduces the time and the complexity greatly in the than the classical case. And that algorithm is called the Deutch-Jozsa algorithm, and I'll be doing that in a different video.